2.3, number 102, I guess. 102. This is the use of the conjugate. It's an important algebraic technique to find the answer to limits that usually involve some sort of radical. It doesn't have to be radical, but very commonly it is. So let's go through it. Limit as x approaches -3, and we have the root of x plus 4 minus 1 above over x plus 3. So again, we inspect it and we see what happens as x approaches -3 in the numerator and denominator respectively. As x goes to -3 in the numerator, you will have -3 plus 4 inside the radical, which is 1. And the root of 1 is, of course, 1. And 1 minus 1 is 0. So the top overall is heading towards 0. And the bottom, obviously, is heading towards 0. It is another 0 over 0 indeterminate form. Which means, from my perspective, there's hope for finding the answer, especially in textbook problems. So, in this case, it would not be at all obvious if I hadn't shown you, but after I show you, it will be obvious from henceforward that the appropriate measure to take is the use of the conjugate. I'm going to rewrite this. There. What is a conjugate? Well, a plus b is the conjugate of a minus b. And a minus b is the conjugate of a plus b. It works both ways. In other words, all you do is switch the sign between the two terms in the sum or difference. So when I say I want to use the conjugate here, I mean the conjugate of the numerator. Right? I'm going to multiply top and bottom by that. So multiply top and bottom by x plus 4. Again, I'm changing the sign between the terms, not inside a term. So plus 1 here, and the same exact expression on the bottom. That way I'm not changing the value of this function. I'm going to merely change its appearance. And actually what I'm doing is irrationalizing the numerator. It will irrationalize the denominator, but that's fine, right? It turns out this will give us exactly what we want. So, when we multiply two conjugates together, right, a plus b times a minus b is, of course, a squared minus b squared. And that's helpful to know. Right? It's simply difference of squares in reverse, right? Usually you have a difference of squares, then we should factor, and you factor into this form. Here we have a product of two things that look like this. There's a minus b, here's a plus b. I want to multiply them together. The bottom I would never multiply out. In reality, I'm just going to write the x plus 3 factor by this larger denominator factor in the next move. So here we have limit x approaches -3. Of denominator is just x plus 3 as I described, multiplied onto this, that conjugate expression. And the numerator I do want to multiply out. This is going to reveal a hidden factor. And since we know that both of the numerator and denominator approached 0 as x approached -3, it is pretty certain that there should be a hidden factor of x plus 3 appearing up here, which will cancel with this one. Okay? So if we just use this approach here, that a minus b times a plus b is a squared minus b squared, then I should simply square this, which would of course just be x plus 4. You're just squaring the square root, so you get the argument. And then I should have 1 times 1 is 1, so minus 1. There is a squared minus b squared. Right? Again, I'm viewing this as a and this as b. But x plus 4 minus 1 is, of course, x plus 3. So they cancel. I'm going to go ahead and cancel them right here instead of writing a whole new step. There. All right, so now the limit looks like x approaching negative 3 of 1 over our conjugate, x plus 4 plus 1 down there. But now, as x approaches negative 3 in this expression, what will happen? I will get the radical of negative 3 plus 4, which is 1. 1 plus 1 is 2. The bottom is no longer heading towards 0 because I removed that factor that was causing it. So now it should be a simple direct substitution case. I'll just plug in the negative 3 value because this function is now continuous at negative 3. So we have 1 over, like I described, the root of negative 3 plus 4 and plus 1, and that's what I said, it is a half, and that is our limiting value. So again, the 0 over 0 case indeterminate form was hope, especially in textbook problems. There's usually a lot of hope. There's our answer right there, it's 1/2. Again, what happened? The 0 on top, which is trying to force the fraction, right, this ratio, down to 0, did not win because the limit was not 0. The 0 on the bottom, which is attempting to cause this ratio to explode towards infinity, right? As the bottom gets smaller, the overall ratio gets larger. It did not win because this did not become infinitely large. And it turns out they counteracted each other in some way, which is hard to describe, but ultimately ended up with a value of 1/2 as they worked together.